So, if the sun is this giant, relentless nuclear space heater, basic logic dictates that we should be sweating the most when the Earth is physically closest to it, right?
Yeah, you would think so.
Like if you walk up to a bonfire, the proximity is what dictates the temperature. But engineering a functional solar grid relies on the exact opposite being true.
It really does, which is fascinating.
It is. So, welcome to today's deep dive. We are jumping into a comprehensive engineering textbook covering renewable power plants.
And this is such a great source text.
Yeah, our mission today is to decode the actual cosmic mechanics, the hard physics that make capturing solar energy possible. We are bypassing the standard surface level talking points to look at the actual math.
Right, from the macroeconomics of global supply chains all the way down to the specific calculated angle a piece of silicon needs to sit on a roof to catch a moving cosmic target.
Exactly. And it is a phenomenal source text for that exact reason. It strips away all the ideological debates and just looks at renewable energy as a pure engineering challenge.
Right, like how do we take this staggering amount of ambient radiation, capture it efficiently, and then stabilize it enough to power an industrial grid?
Okay, let's unpack this. Because before we get to the physics of photons and orbital mechanics, the textbook actually anchors everything in the wallet.
Which makes sense. Economics drives the engineering.
Right. For decades, the primary hurdle for renewables wasn't really the technology, it was just the financial penalty. But looking at the data from the text, it highlights this severe market disruption right around 2015.
Yeah, that was a huge turning point.
We saw the price of solar power just plummet to an unprecedented 4 cents per kilowatt hour. This was at a massive plant in Dubai developed by Aqua Power.
And, I mean, that 4-cent threshold is essentially the event horizon for modern energy markets.
Wow, really?
Yeah, it represents the exact moment parity was achieved.
Hmm.
And not through, government subsidies, but through just brute force economies of scale.
Okay, so what actually drove that price collapse?
Well, it was a maturation of the polysilicon supply chain and automated manufacturing. Combine that with developers like Aqua Power structuring these massive long-term power purchase agreements, and, well, that de-risked the upfront capital expenditure.
And the text points out it wasn't an isolated incident for solar either.
Right, wind power did the exact same thing.
Yeah, wind hit that exact same 4-cent milestone in Egypt that very same year with a 250 megawatt EDF wind farm. So the manufacturing bottleneck just kind of broke across multiple technologies simultaneously.
It did. But, beyond simply matching fossil fuels on price per kilowatt hour, generating power locally introduces a massive structural advantage for the grid itself.
Because it changes how we distribute power, right?
It fundamentally changes the topology, yeah.
Yeah.
Traditional power generation relies on these highly centralized plants like massive coal or nuclear facilities.
Right.
And they are pushing high-voltage alternating current across hundreds of miles of transmission lines.
Which has to be inefficient.
Oh, entirely. The physics of moving electricity over those distances dictates massive line losses, not to mention the billion-dollar right-of-way disputes just to build grid extensions.
So generating power closer to the point of consumption bypasses that whole archaic infrastructure.
Exactly.
You essentially stop paying shipping and handling on your electricity.
That is a great way to put it.
So looking at the global landscape, the text provides a snapshot from 2013 that shows who was anticipating this shift early on. And China was sitting at a staggering 378 gigawatts of renewable capacity.
Right. But if we connect this to the bigger picture, that 378 gigawatt figure requires a little bit of context.
How so?
Well, in 2013, China's numbers were heavily buoyed by their legacy top-down infrastructure model.
Yeah.
Specifically, massive hydroelectric projects like the Three Gorges Dam.
Oh, right. Hydro counts as renewable.
Yeah, and rapid wind deployment across the Gobi Desert. They utilized their vast, varied geography to scale mature technologies while they were secretly domesticating the solar supply chain in the background.
Which obviously set the stage for their current dominance.
Exactly.
Following them in that 2013 data, the U.S. was at 172 gigawatts, Germany at 84, India at 71, and Spain and Italy tied at 49.
Those were the early major players, yeah.
But, no matter which country is deploying the hardware, the underlying fuel source is the exact same. To understand the engineering bottleneck of solar, we really have to look at the engine driving the entire system.
The sun.
The sun.
Yeah, and the sun basically operates as a continuous, uncontained fusion reactor. We are not dealing with a chemical fire here.
Right, it's not actually burning.
No, not at all. The core of the sun is this incredibly high-pressure environment where hydrogen nuclei are violently crushed together to form helium.
Which is fusion.
Yes. This proton chain reaction converts a tiny amount of mass directly into just an incomprehensible amount of energy.
And that energy radiates outward, eventually bombarding the Earth's surface with roughly 1,000 to 1,300 watts per square meter.
Which is a massive amount of raw material.
It is. But this brings us back to that counterintuitive reality of our orbit that we mentioned at the start. We are trying to catch a massive amount of radiation, but the Earth is not traveling in a perfect circle.
No, our orbit is elliptical.
Right.
There's a specific point called aphelion, where the Earth is at its absolute furthest distance from the sun. And for the northern hemisphere, aphelion occurs squarely in the middle of summer.
Which runs completely counter to basic intuition.
It really does.
If we are physically further away from the fusion reactor in July, we have to look at the mechanical reason why the northern hemisphere is experiencing peak thermal heat.
And the answer there is axial tilt.
Okay, break that down for us.
Well, the Earth rotates on an axis tilted at approximately 23.5 degrees relative to our orbital plane. So while we might be further away from the sun in space during the summer, that 23.5-degree tilt angles the northern hemisphere directly toward the incoming solar radiation.
Let's visualize the actual insolation density here, because the text uses a great analogy.
The flashlight analogy, right?
Yeah. If you shine a light at a glancing angle across a sphere, those photons spread out, losing their intensity over a wide surface area.
Right, they just scatter.
But because of that summer tilt, the northern hemisphere intercepts the solar flux almost perpendicularly. The photons are densely packed per square meter.
Exactly. That direct, concentrated strike of radiation, combined with the longer daylight hours caused by the tilt, is what drives summer heat. It entirely overrides the fact that we are physically further away in space.
It's all about the angle of the hit.
Yeah, and that perpendicular strike is the holy grail for a solar engineer. Conversely, during winter, the Earth reaches perihelion.
Which is its closest point to the sun.
Right. But the northern hemisphere is tilted away, so the solar flux hits at a harsh oblique angle, the energy scatters, and, well, you get winter.
So you have this relentless thermal output hitting a planet that is not only tilted but actively wobbling through an elliptical orbit. That creates a massive geometric headache for any engineer trying to build a static power plant on the ground.
Oh, absolutely.
How do you orient a stationary piece of glass to maximize photon capture against a moving cosmic target?
Well, the textbook establishes a foundational directional rule right off the bat. If your array is located anywhere in the northern hemisphere, whether that's those aqua power plants in the Arab states or just a roof in North America, the panels must orient south.
Always south.
Always.
Yeah.
That catches the sun's ecliptic path across the sky.
Okay, facing south gives you the baseline exposure, but I have to push back a little on the idea of a fixed tilt.
Okay, how so?
If the sun's elevation is drastically shifting between the summer solstice and the winter solstice, bolting a panel down at one static angle just guarantees you are losing efficiency for half the year, doesn't it?
Well, what's fascinating here is how the text applies a surprisingly elegant mathematical formula to calculate the optimal fixed tilt. And you don't even need complex seasonal adjustments.
Really? How does it work?
It relies entirely on the geographic latitude of the installation.
So the math changes depending on how far north of the equator you are?
Precisely. If an engineer is setting up a fixed array for optimal performance during the spring and autumn equinoxes, the rule of thumb is to set the tilt angle exactly equal to the geographic latitude.
So a plant at 30 degrees north latitude gets a 30-degree tilt.
Exactly.
That establishes the median. But what about optimizing for peak summer or winter?
For a summer-optimized array, when the sun is tracking much higher in the sky, you flatten the angle. You just take the latitude and subtract 15 degrees.
Oh, I see. So that same 30-degree array drops to a flatter 15-degree tilt to catch the high noon sun perpendicularly.
Right. And for winter optimization, when the sun hangs really low on the horizon, the panels need to stand up straighter to intercept those glancing rays.
So you add 15 degrees.
Yep. The formula is latitude plus 15 degrees, pushing the array to a steep 45-degree angle.
That math works flawlessly for a static array on a residential roof. But when we look at the industrial scale, manual adjustments are impossible. You aren't dispatching crews with wrenches to recalibrate a 5 million panel farm 4 times a year.
No, definitely not.
Yeah.
Which is why utility scale engineering abandons the fixed tilt limitations entirely.
They use moving parts.
Yeah, they utilize automated sun tracers or solar trackers. These use single-axis or dual-axis mechanical actuators to constantly pivot the array.
So they actually follow the sun across the sky.
Exactly. They follow the sun's azimuth from east to west throughout the day, and they adjust for elevation. It ensures the angle of incidence remains mathematically perfect from dawn to dusk.
I mean, you introduce mechanical complexity and wind load challenges with moving parts, but you squeeze every possible drop of maximum power out of the daylight hours.
It is a trade-off, but at that scale, it is worth it.
Okay, so we know the geometry now, but let's talk about the hardware actually doing the conversion.
Yeah.
We're all familiar with standard PV or photovoltaic technology, but the text points out a severe bottleneck at the semiconductor level.
Yeah, this is a major limitation. Photovoltaic cells rely on the photoelectric effect.
Which is what exactly?
Basically, incoming photons knock electrons loose within a semiconductor material like silicon, and that creates a direct current. But there is a hard physical limit here.
How much can they actually capture?
The text notes that PV currently captures only about 10 to 15% of the sun's energy per square meter.
Wait, if we are getting bombarded with up to 1,300 watts per square meter and PV's only capturing 15% of that, where is the other 85% going? Does it just vanish?
It is lost primarily as heat.
Just heat.
Yeah. The incoming photons either don't have enough energy to dislodge an electron, which is known as the band gap limit, or they have too much energy, and that excess is shed as thermal waste.
Which probably isn't great for the panel.
No, it actually heats up the panel and reduces its efficiency even further.
So you have a technology with a naturally low ceiling.
Right.
The alternative the text explores is CSP, or concentrated solar power, which completely ditches the semiconductor approach, right?
It does. CSP embraces the thermal heat rather than fighting it. Instead of converting light directly to electricity, CSP utilizes vast arrays of parabolic troughs, or automated heliostat mirrors.
To bounce the light.
Exactly. These arrays focus massive amounts of scattered solar radiation onto a single central receiver, often a tower containing molten salt or a synthetic oil.
You are creating an intensely localized thermal focal point.
Right. It heats the transfer fluid to extreme temperatures, which is then used to boil water, create steam, and drive a conventional mechanical turbine.
Like a traditional power plant, just with sun instead of coal.
Yes. And the distinct advantage of CSP is thermal inertia. Molten salt retains heat for hours, allowing a CSP plant to continue generating turbine power long after the sun is actually set.
Now, here's where it gets really interesting, though. Because PV is capped at that 10 to 15% efficiency rate, developers can't rely on density to generate power.
No, they have to go wide.
Right. To generate utility-scale power, they have to compensate with a sheer, sprawling geographic footprint.
And the textbook details some massive examples of this.
Yeah, like the Agua Caliente solar project in Yuma, Arizona, built by First Solar. It covers 9.7 square kilometers of desert landscape just to achieve a 400 megawatt capacity.
The footprint is staggering, yeah. But the architectural topology of the plant is what really stands out to me.
Because they didn't use standard silicon.
No, they didn't.
The text notes they deployed 5 million individual thin film panels. Let's clarify why First Solar went that route. Thin film panels, like cadmium telluride, are generally even slightly less efficient than standard silicon. Why use them?
Because of the manufacturing scale. Growing and slicing silicon in gigs is an energy-intensive, batch-based process. But thin film is deposited continuously onto glass substrates.
Oh, so it is just way faster to make.
It is incredibly cheap and fast to produce. When you have 9.7 square kilometers of cheap desert land, you don't need peak efficiency per panel. You just need a massive volume of ultra-cheap panels.
But the engineering nightmare has to be the wiring.
Oh, absolutely.
I mean, each of those 5 million thin film panels produces a tiny trickle of direct current, just 75 to 77 watts each. You have to wire millions of individual DC trickles into massive string inverters, step up the voltage, convert it to alternating current, and synchronize the frequency before it can ever touch a transmission line.
It is an exercise in massive parallel aggregation, and the blueprint is replicating globally. The text highlights the Charanka solar park in India, reaching a 300 megawatt capacity across 19.8 square kilometers by late 2014.
And that required a $280 million capital investment.
Right, which again pencils out economically when the levelized cost of energy drops low enough.
We also see the Huang Hydropower Golmud Solar Park in China's Qinghai province. That held the title of the world's largest PV plant back in 2011, with a 200 megawatt capacity over 5.64 square kilometers.
Yeah, the scale's just hard to wrap your head around.
But creating the power in a desert is only half the equation. You actually have to integrate it into the wider world.
Right, integration dictates the final architecture of the system. And the textbook categorizes this into two primary avenues. The first is the standalone or off-grid system.
Which is completely decentralized and isolated from regional transmission lines.
Exactly.
Now, if you are off-grid, the immediate assumption is that you need a massive, expensive bank of lithium-ion or lead-acid batteries to act as a buffer for when the sun goes down.
And batteries are the standard, yeah. But the text highlights a highly elegant workaround where energy storage isn't required at all. It comes down to matching the electrical load directly to the solar resource.
Okay, explain how that works without a battery.
Take an agricultural water pump in a remote area. The goal isn't to have power 24/7, right? The goal is just to move water into a reservoir.
Okay, that makes sense.
So you wired the PV array directly to the DC motor of the pump. As the sun rises and the insolation increases, the pump spins faster. When clouds roll in, it slows down. At night, it stops completely.
Oh, wow. So the system is perfectly synchronized with the diurnal cycle.
Yeah. And the water reservoir itself acts as the battery, storing the kinetic work.
That is just brilliant application-specific engineering. You eliminate the most expensive and chemically volatile component of the system just by rethinking the end goal.
Exactly. But for residential or industrial zones that demand a constant 60 hertz AC baseline, for TVs and refrigerators, you need the second model.
It's a grid-connected system.
Yes. This is where a solar farm, or even just a rooftop array, is wired through an inverter directly into a local distributor network.
So what does this all mean for the homeowner?
Well, the grid basically acts as an infinite battery. If a home array produces a surplus of current during peak afternoon insolation, the inverter pushes that excess power backward through the meter onto the local grid.
Instantly decentralizing the neighborhood's power supply.
Exactly, and taking the load off legacy power plants.
And when we step back and look at the entire sequence mapped out in the text, the scope of what is actually happening when you turn on a light switch powered by renewables is profound.
It really is.
You are interacting with the end result of a proton fusion reaction happening 93 million miles away. That thermal energy crosses the vacuum of space, intersects with the planet tilting at 23.5 degrees while it navigates an elliptical orbit, and strikes a vast field of cadmium telluride glass in a desert.
It sounds like science fiction when you say it all at once.
It really does. We use automated azimuth trackers to maintain the perfect angle of incidence, force photons to dislodge electrons across a semiconductor band gap, invert that direct current into a synchronized alternating wave, and push it through a localized grid straight to your living room.
Because engineering doesn't just harness the natural world. It translates cosmic phenomena into standardized industrial utility.
Beautifully said. Well, thank you for joining us on this deep dive. Our goal is that the next time you walk outside and feel the intense heat of the summer sun, you bypass the assumption that we are simply closer to a fire.
Right. Hopefully you see it differently now.
Yeah, we hope you visualize the axial tilt, the orbital mechanics, and the sheer density of photons bombarding the surface, recognizing it as a massive, continuous fuel source, just waiting for the right geometry to catch it.
This raises an important question to leave on, though.
Oh, what's that?
Well, we established that the physics of current PV technology artificially caps our capture rate at 10 to 15%, right? Which forces us to build those sprawling 10 square kilometer mega plants to compensate.
Yeah, the massive footprint.
Right. Imagine what happens to the global energy market, to urban architecture, and to grid topology if a material science breakthrough suddenly pushes that semiconductor efficiency to 40 or 50%.
Wow.
If the energy density of a single solar panel triples, how does that redefine the limits of where and how human beings can live?